We have seen that in Gaussian elimination, we are always dividing by pivots. So if pivots are 0, then certainly Gaussian elimination will fail. But even when pivots are not 0, they are small, they will create lots of issues. And these issues usually originates from the round of error. Round of error comes from the fact that a computer is a finite precision machine. So when we are trying to implement real number arithmetic in a computer, the computer certainly will truncate the real number after certain digits. So there is always an inherent round of error in computation. Now these round of errors are enhanced if they are divided by a small number, and in Gaussian elimination the small number is the small pivot. So if we have a small pivot and if we have a large enough round of error, that leads to instability in solution. By instability we mean that a small round of error will generate large error in the solution. We know that the computational result cannot be exact, but we always hope that small round of error will lead to small errors in solution. When it becomes so that small round of error leads to large error in solution, we call that solution to be unstable. Therefore, to impart stability, we try to make sure that the pivot element, that is AII, must be greater than all other elements that is lying just below the pivot elements in the same column, which we can write here AII, absolute value of that should be greater than or equal to AKI for k greater than I. Now you recall that we were discussing this Ax equal to B system, and this Ax equal to B system leads to Ux equals B prime after forward elimination, and forward elimination uses this elementary matrix multiplication. We'll now see that partial pivoting will bring new elementary matrices which we are writing P. These are the same as E otherwise. They are only thing that these P matrices are permutation matrices and they are responsible for swapping row. This entire operation that we have just described, we call that partial pivoting. And let us see how we actually do partial pivoting, and even before that we have to see that why we really need partial pivoting. As we were talking about, that as soon as we try to implement real numbers in a computer, the real numbers will be always rounded off. After certain digits it will be cut off. Now how many digits we are using in our calculation? Usually they have significant effect. That is why we try to use high precision in numerical computing. And we will now see that what happens when pivots are small. What do they do of these approximations which are coming from rounding off real number? Another point here, you have to understand that this idea that this round of errors will be amplified by small pivot is not really visible initially, because initially your pivots may look big, but then we keep on computing, and with forward elimination all the pivots other than this one will keep on changing. So we have to check the pivots are small or pivots are reasonably large after every step in the forward elimination. So this idea of small pivot amplifying round of error is applicable for the entire range of computation, not only for the initial state. So we have to keep on checking it over and over. Let us take a very simple example. Here I have a 2 by 2 system. The first equation is 3 into 10 raised to minus 4 x1 plus 3 x2 equals 2.0001. And the second equation is x1 plus x2 equals 1. Here I am writing these point zeros only to emphasize that we are dealing with real numbers here and not integers. Now we know that if we want to do Gaussian elimination, this is a very simple system, but we have to do something in the row 2. I will have a new row 2 which will be equal to my old row 2 plus certain factors multiplied by row 1. Now what is this factor? We know that this factor comes from 1, that is the coefficient of x1 in equation 2, divided by the pivot element here. The pivot element is 3 into 10 raised to minus 4. That is the A11 element or the pivot element here. Now when we carry out this forward elimination, this particular operation on row 2, what we get is this. There is no change in the first row or the first equation. In the second row, of course, the first element is now 0. The second one is minus 9999. On the other side, we have minus 6666, which means that I have a x2 of 6666 divided by 9999. Once I get this as my x2, I should be able to find x1 from my equation 1, and my x1 is 2.0001 minus 3 multiplied by x2 divided by the pivot once again 3.0 multiplied by 10 raised to minus 4. Now it's very easy to check the exact solution here. The exact solution is x2 2 by 3 and x1 1 by 3. You can check this exact solution by putting this value of x2 and x1 in the original equation. Now let us see what happens to the numerical solution. My x2 is 6666 divided by 9999. You may think that, well, it is becoming 2 by 3, but we are not implementing it as 2 by 3. We have to implement it as real number. And when we implement x2 as real number, then we have to cut after certain digits. So let us see what happens when we cut x2 after certain digits. So here for the first trial, I cut x2 after 3 digits, which look quite reasonable. 3-digit arithmetic we do quite often. But then you take this 0.667 and you put in here for x1 calculation, and you find an x1 of minus 3.33, which is absolutely bizarre. It is far away from the original x1, exact x1, that is 1 by 3. Then if I improve on x2 and I put 4 digits, then I see that my x1 is coming to be 0. It is once again an absolutely wrong answer. I then put one more digit in x2 and my x1 is now 0.3. It's much better, of course, but it is still, if you think that at least it would be correct up to few decimal points, it is not there yet. Then I go on and I increase one more digit. So now I have 6 digits in x2, and then I see that I have x1 0.33. That means it is correct up to 2 decimal points, which you may be satisfied or you may not be satisfied. In many cases we wish that it should be okay, more than 2 digits. So if you are looking for some sort of an accuracy of 3 or 4 digits, then we are not there yet. So you have to take x2, even more digits in x2 to get a better approximation in x1. So we can clearly see the problem here. Why this problem is happening? This problem is happening because the inaccuracy in x2, some inaccuracy in x2 will always happen because we have to round up somewhere. And now that inaccuracy is being amplified by this small pivot. I have this 10 raised to minus 4 here. This small pivot is amplifying this small inaccuracy, so my result is absolutely inaccurate. So now what can you do about it? To do this, we wish to implement what we call is partial pivoting. And what it is? In partial pivoting, what we do is fundamentally is row swap. So the top row will come at the row 2 and bottom row, that is row 2, will become my new row 1. So this is going to be the result of this row swap. After this row swap, if I now continue the same type of Gaussian elimination operation, I have to use this row 2 equals old row 2 plus certain factor into row 1. But now this factor is the coefficient of x1 in equation 2, that is 3 into 10 raised to minus 4 divided by the pivot. The pivot is now 1. So it's a good pivot now. And I can see that the factor is pretty small here. If I allow this operation, then after the forward elimination, I have this 1 and 1, 1 at the top and 0, 2.9997, x1, x2, 1, 1.9998. And if we do so, I have this x2 as 1.998, 2.997, and x1 is 1 minus x2 divided by 1. So it is simply 1 minus x2. Let us see what happens here. The exact solution, of course, it does not change, but we can see that x2 with 0.667, I have x1 0.333, 0.6667, I have 0.3333. So if I keep on increasing the precision in x2, my precision in x1 also increases. So we are in a good standing now. So now we can see that in previous example, the small pivots were amplifying the round of error. Here we have large pivots which are suppressing the round of errors. Now the goal is to do a proper partial pivoting for an n by n system. And the idea here that whenever we start the forward elimination operation with AII, we want to have whatever element below that AII to be less than AII. We have to make sure that it is happening not only at the initial stage, but also at all subsequent stages. This is very important. Whenever we are using AII as a pivot, we have to check it. So let's see that how we can do so. So for instance, when we are starting this, we are starting with our first pivot A11. What we want to see here, how does this A21, 31, etc., as compared to A11? So we have to scan through this entire column and we have to identify this K. What is this K for which this AK1 is greater than or equal to all other AI1? That means AK1 must be greater than or equal to all the elements in this column. Once we scan this, we have to check that what is the value of K. If K is 1, then I can see that A11 is the biggest and I have no problem. Actually, I can go ahead with the forward elimination. But if K is not equal to 1, then what? Then what I'll do, let's say my kth row is here and this is my 1 row. So what I'll do a swap between K and 1. This kth row I'll put it at row 1 and 1 row will come at the place of kth row. This is how my A11 will remain the biggest in that particular column. Once we do this swap, we can then continue with the usual forward elimination procedure, and we make the ai1 equals to 0 for I equal to 2 to n. That is the usual forward elimination procedure. We can follow that. Now this gives us the first column here to be all zeros. But then we go for the second column and we start A22 as my pivot. And once again, we have to repeat this procedure. So in A22, once again, we scan from A22 to AN2 and we identify the kth row for which this AK2 is greater than all other element in that column. We identify that K. If K equal to 2, then we know that A22 is the greatest and we are fine. If it is not, then we have to swap between row K and row 2 here. Once that swapping is done, we will continue with our forward elimination. And this is the way we will go for column 3, column 4, etc. You recall that at the end of forward elimination, we have this sort of a system which is in matrix form. We can call that we have reached an upper triangular matrix. And how we reach this upper triangular matrix? You recall that we have discussed that we go through by elementary operation. So we multiply by E matrices, elementary matrices, both sides of this equation, and U becomes this elementary matrices multiplied by A, and B becomes the elementary matrices multiplied by B. And now we can see that over and above this elementary matrices, in partial pivoting, we have to do this row swaps probably many times. If we do row swap, that means elementary operation and the multiplication with a matrix like this. Here, this is a matrix, what we call a permutation matrix. This is also an elementary matrix, but this particular form is called permutation matrix. Permutation matrix is very much like an unit matrix. Only thing that in some of these places 0 and 1 are removed. So in every row there will be 1, 1 and rest 0. Similarly in every column there will be one number of 1 and rest 0. So that is something is permutation matrix. So this is a typical example of a permutation matrix. If I use this permutation matrix for my elementary operation, I multiply with any other matrix. If this matrix, permutation matrix, is pre-multiplied to A, then this row and this row, this blue and green rows will be interchanged and nothing will happen to any other rows, because in all other rows we have all zeros and 1 at diagonal. So nothing will happen with multiplication. Only thing that will change is this green and this blue rows. They will interchange or there will be swap. So when we do partial pivoting in a large matrix, probably we are doing these row swaps many times. Every time we do a row swap, we are essentially multiplying with a permutation matrix. Permutation matrix is doing a row swap. So if a permutation matrix is pre-multiplied with another permutation matrix, then what is happening that it is doing a row swap in that permutation matrix, which means that it still remains, the product still remains a permutation matrix. So think about it, that why it is so, and convince yourself that the products of permutation matrices will be also a permutation matrix. So the elementary operation that we write to show the Gaussian elimination in matrix form, now we can write that in general, because we are doing the row swap as well for partial pivoting. So the elementary operation we can write in general as this E matrices multiplied by PA. This P is a permutation matrix. In fact, this may be a product of many permutation matrices. And similarly, the B prime is the same E matrices and the same P, that is the product of many permutation matrices probably, and multiplied by the original column vector B. So this is how our original idea of showing Gaussian elimination in form of elementary operation in matrices, we can show it now when we are implementing partial pivoting. So now what you can do, you probably already have a pseudocode of naive Gaussian elimination, that is the usual Gaussian elimination with nothing else. Now you take that naive Gaussian elimination pseudocode and you include partial pivoting in that pseudocode. If you have written a computer program of this naive Gaussian elimination, now you go back to that computer program and you implement partial pivoting in that naive Gaussian elimination program. So that's all for this lecture. Thank you, and I'll see you in next class.